Welcome to Einstein's Mechanics. In today's episode, we are going to look at rectilinear kinematics. So, in this first episode, we are looking at continuous motion in a straight line. Are we okay? So, let's get into that. So, before we do some calculations, let's look at the definition of terms such that when we use them, we'll be able to understand what we are trying to say. So the first term that we are going to talk about is position. So what does it mean when we say the position of a particle? So let me write it. So we have the position. The position of a particle is basically the location of the particle from a fixed point. So we can talk of a position is the location of a particle. So we are interested in location of a particle from a fixed point. And mostly this fixed point, we call it as what? The origin. Are we okay? So, for example, if I have this, and this is my origin O, and I have a particle at this point. So this is my particle. So if I want to know the position of this particle, the reference is from the fixed point, which is O, the origin here. Are we okay? So now I can trace the origin to the position at the right side. So this is going to the positive side, and I can also trace it to the negative side. Are we okay? So the position of a particle is basically, we denote it by x. So this will be the position from the fixed point or the origin. Are you okay? Let's pay attention that it can be negative and it can also be what? Positive for the position. One thing that we have to also know that this position that we are representing by x is measured in meters, where we have our m, or it is also measured in feet, where we are going to have our ft. Are we good? So this is the explanation on position of a particle. The reference is from the origin part to wherever it is being located. Now let's look at displacement. In our studies, if we come across the word displacement, then displacement is basically the change. Are we okay? The change in position. So change in x. The change in position. That is basically what? Displacement. So, for example, if the same graph as from the first one, I'm having the particle from the origin. Please remember displacement is change in position and position is the reference from the origin. So initially, my particle is at this point and I have the direction to that place as my x. So this is the position. But few time later, I notice that the particle is at this point. Are you okay? And I'm going to have another position here for the same particle. So this is the second position. I will call that as S prime. So what do we see? We can see that at this interval, the particle has changed in position. It has caused a change in X. And this change in X is as a result of x1 minus x. So this is what we refer to as the displacement, the change in the position of a single particle that we are considering. Are we okay? So it is also just distance, or it is just position minus position. So it is also going to be measured in what? Meters or feet. Let's pay attention. Since the position is either a negative or a positive value, meaning displacement, which is change in position, can also be what? positive or it can be negative depending on what the parameters are. I told you that movement to this direction is positive and anything to the left of the origin is negative. Pay attention to that because we are going to use it. Then also displacement is a vector quantity. It's a vector quantity, meaning it has magnitude and direction. Are we okay? All right. Now, the third term is velocity. Now we'll come across the word velocity. And what does velocity also mean? So velocity is basically the time rate of change of displacement. So you can see how there is a change in each of them. So now we use position to find displacement. Displacement is helping us to get the velocity. So velocity, where we are going to call as V, or let me say V average, is the time rate. When we talk about time rate, it is what? The rate at which a particular quantity, in this case displacement, it's changing with time. Are we okay? So if I say the time rate of change of area, that is going to be area on time. The time rate of change of, we have length, that is going to be length on time. So here, the time rate of change of displacement, where we know displacement is change in distance, that means it is going to be change in distance on change in time. There we go. So this is velocity. All right, so since we have a change, we can represent this in calculus as a change in x on a change in t. You will get that. So this will give us our velocity or the velocity average. Let's look at this from this graph. We can also get it this way, where this is s. Remember, all these are s, and this is s. Now, if we have it drawn, we know that here is our origin. Let's use this. Particle is at this point, later it is at this point. So at this point it has a velocity v, and at this point it is also moving with a velocity v1. Remember, it is going to change its position from this first position to this second position, so meaning there has been a change in position. Before it changed position, there was a time interval, change in time. If here it was say at 2 seconds, it is going to be here, let's say 4 seconds. So there has been a change in 4 seconds minus 2 seconds, right? So the change in distance or position, which is change in x, over the change occurring in time, the 4 seconds minus the 2 seconds, is basically what we refer to as velocity. It is quite simple. So this is the simplest explanation on velocity. Now, let's look at acceleration. How do we also talk about acceleration? It is also very simple. Now, when we talk about acceleration, it is, so the next part is acceleration. Remember, acceleration and deceleration, they are all referring to the same thing, just that deceleration means the negative form of what? Acceleration. So acceleration basically means it is also the time rate of change of the velocity. There we go. So when we cause a time rate change in the velocity, we are also getting the acceleration. So simple acceleration average. It is also, we saw that velocity is v, so a change in the v over the time rate, the change in time, is basically the acceleration. So in calculus, we are going to have dv on dt to be this way. We can represent this on a graph again to look like this. Remember, everything is going to be from a reference point because it is going to start from position s to go to displacement change in position to go to velocity change in displacement. So this is displacement, this is position, and change in t, this is velocity. 2, change in velocity, change in time, this is acceleration. Are we okay? So the particle is still going to be at a point here and it will change. So at here too, it has a velocity. At this point, it has a velocity. This is s. So the change of the velocity is going to be the acceleration that occurred over here. Are we good? Now, an interesting part about the acceleration, you know that acceleration is the change in what? V, on changing. So this is change in V over change in t, which is the V on the t. But we can directly get the acceleration from the position, which is going to be the second derivative of the position and the second derivative of the time. Are we good? Well, we will solve a problem and we will see how best this is going to work. So this is for the acceleration. Remember, acceleration can also be positive or negative. And I told you that the moment it is negative, then it becomes a deceleration, meaning it is decreasing in its acceleration. So if here the direction is looking in the positive direction, then so it is accelerating. For deceleration, it is going to look this way so that we can see that it is decelerating. Are we okay? All right, so this is what we have. It is also measured in meter per second square or feet per second square. Pay attention to the units because it will help you define your parameters. Now, since we are talking about motion, there is a place or there is a possibility of having functions. When I say functions, it is going to be functions of time. Instead of them to locate the position of a particle, say this is the particle, it is maybe 2 meters from the origin, we can give you that the position is x, it is 2t from the origin. So this is what I call function. Instead of getting the velocity to be, say, 2 meters per second from the origin, we can give it to you as it is 2t plus 4 from the origin or from a particular point. So what if we have a function of the parameters? Now, if we have functions, then we are going to look at it this way. Now, always we know it is from position to change in, that is displacement, to change, that is velocity, to our acceleration. So meaning if we start from the acceleration, remember in calculus, integration means if we integrate the acceleration, we are coming back to the velocity. We integrate it, we come back to that, and so on. Are we okay? So here we can say that from our A, which is dv on dt, which is also a constant, we can integrate for the various functions. So what I mean is a situation where I'm giving my acceleration as say 2t plus 4. I can use integration to derive my velocity, to derive my displacement from the acceleration function. And we are going to work with that a lot. So let's see how we will do that. So in situations like this, when we talk about the velocity, we're going to see how we can integrate or get back the velocity. So for the velocity, what we are going to do is that we know that acceleration is the velocity with time. When we differentiate the velocity, we are getting the acceleration. And so if we apply integration, then we are going to get back our v. So here we are interested in this v. So what we will do is that we can say dv is equal to a dt. Yes, if you make dv the subject, this is what you are going to get. Now we apply integration. But here we are going to apply definite integrals, right? So here what we are going to start here is we are integrating v from 0 or from v is equal to 0 up to v. And here we are integrating with time from a time 0 up to a time t. And when we integrate this, our v, which is the velocity, is going to be a certain v naught plus a certain act. So this is an equation that we are going to get, right? So in situation where you are going to get the velocity, they will give you the acceleration function and you integrate to get the velocity function. This is not what you are going to get, but from what we are deducing, this is a function that we are getting. Are we okay? The same thing, we can consider the position, where we are calling as what? S. So the position to what we know is that we have velocity to be equal to, when we differentiate the position with time, we are getting the v. So now we are interested in the position, which is ds. So we can say dx is equal to v dt. Then we apply our integral. This is going to be x from a point 0 up to a point x, and t from 0 to a point t. And when we perform this integral, we are going to get a function in this form, where we are going to get our s is equal to a certain s naught, which is s at the 0, plus v naught t plus half act squared. So from this is what we are getting. Are we okay? So meaning if we also integrate the velocity function that we got from the acceleration, we are going to get back a displacement or a position function. So this v, you can put this at the part. Are we good? So this is basically an example showing you how we can get the various parameters by integration. Are we good? So let's look at how we are going to get it. So acceleration, let's write our final thing is dv on dt. We also know that velocity is dx on dt, and we are going to get our s function as a function of what? Time. Are we good? The same way, if we are interested, we can say that when we integrate s is equal to the integral of v dt, and our v is going to be the integral of our acceleration dt. Are we good? Remember, acceleration can also be gotten from the second derivative of time with respect to what? The distance. Are we good? Let's solve a practical example so that we can see how best we will go by this. Now, example. The car moves in a straight line such that for a short time, its velocity, its velocity is defined by this function, where t is in seconds. Now determine its position and acceleration when t is 30 seconds. So straight away, we can see that this car is moving. This is the origin. So we have O. Are we good? So it has moved through this position and it is now here, still in motion. So it will cause a change in motion at a particular point. Let's say if here is for 1 second, at 2 seconds it will be here, and at 3 it is going to be here, right? So this is a straight motion, a straight line motion. That's why we are looking at continuous motion that does not change. We assume it to be in what? A straight line. Are we good? All right, we'll talk about those motion that changes, and that will be in other episodes. So here's, you identify your function, which is v as 3t squared plus 2t, and the unit is feet per second, or we can get it as meter per what? Second. So our t is in seconds, and we should find the position, which is x, is unknown, and the acceleration, the a, is also unknown at a point t is equal to 3, where t is 3 seconds. So straight away, we'll check the rules. If we have velocity and we want acceleration, what do we do? First, when we differentiate, so let me first find the acceleration. The acceleration is going to be the derivative of the velocity with respect to time, right? Which is equal to a certain derivative of the function 3t squared plus 2t with respect to what? Time. So the function of acceleration is going to be, we are going to have it as 6t. If you differentiate this function, 6t plus 2. So for the motion, this is its acceleration function, and we are to find the acceleration at 3 seconds. So meaning our acceleration is going to be 6 by 3 plus 2, and that is going to give us what? 20, and the unit is feet per second square. Very good. All right, now we are interested in the position, which is x, and we know that x, to get x from either acceleration or from the velocity, we must what? Integrate. Is that it? Yes. So let's try our integration. So this is what we are going to do. We know that velocity is dx on dt, right? And we are interested in the ds, meaning our dx is going to be velocity dt. We apply integration from x is equal to 0 up to x, from time 0 up to t. Now if you integrate, just this is just like 1 dx, a constant. It is going to just give you the x back, and the limits are x and 0. When you put it in, it will be x minus 0 like this, which is the same as what? X. All right, this is calculus, and you can watch episodes on how to integrate functions. So here, that is going to be integral of 0 to t, and the v function is 3t squared minus 2t dt, right? All right, so if we are to integrate that, that is going to give us a function that we are going to be. So this, if we are to use integration, that is going to be 3 on 3t cubed plus, so that is minus, we have minus here, minus t squared on that, and the integral is 0 to t, which implies that x is equal to, now 3 will cancel out, leaving t cubed minus 2t squared, 0 to t. So if we are to put in the limits, this 0 is going to run everything toward 0. So our x is going to put in t, that is going to be t cubed minus 2. This 2 is going to vanish because it is going to cancel itself. So we are no longer having the 2, and that is going to be 2. So we have the function to be plus. So plus over here, plus over here, plus over here, and that is going to be plus over here, plus 2 square. Are we okay? Now we are interested in finding position when t is equal to 3. So that is going to give us 3 cube plus 3 square, and that is going to give us a final answer. Are we good? So this is how we are going to solve our problems. Are we good? So this, we can punch that 3 raised to the power 3 plus that. Let me punch that and give you the answer. And that is going to be 36, right? Yes. So we have 36, and that is for displacement meters. Are we good? Sure. All right. Thank you for watching this episode. This is just a single example on continuous motion. Check out for the episode 2. We have a lot of problems solved on this linear continuous motion, and I know it is going to be lovely. See you in the next episode. Kindly subscribe to the channel, like, and drop your comments.